All right, let's get started. Can you guys confirm you can hear my audio? All right, thank you all. So hello everyone, my name is David Ruck. I'm here at the University of Maryland in Baltimore, here in Baltimore, Maryland, and welcome to Cytometry in R. So this week we are going to be covering what's inside an FCS file. Now the reason for taking this particular lecture is I have subjected everyone to 2 weeks of very R-focused material, so I want to bring in some cytometry focus since this is a cytometry in R class. So we'll be slicing into an FCS file and see how the different components within there, including the MFI data, the metadata, all these different parameters that are present within those files, how they're stored within a object within R, which we'll know as a flowFrame. So in addition to getting a better understanding of how an FCS file is structured and additional sets of information that we're able to retrieve it will also give us a little building familiarity as far as how we can work with particular objects in R. So if we think back to what we were dealing with for the last couple of weeks, we've looked at a few object types in R, and we're going to add a few additional ones today, specifically vectors, lists, matrices, and data frames. So if we were using the analogy from the last couple of weeks, if every function is a tool, like a hammer, like a screwdriver, like a paintbrush, that's within a toolbox, which would be the actual R package, all these different tools need particular objects in order to carry out their particular function. So a hammer is going to need a nail, it's going to need a wall, just so that you're able to do what you're particularly trying to do with that hammer. Same thing, if you have a paintbrush, you're going to need to paint, you're going to need a wall, just so you're able to paint the wall. So it's very similar if you're thinking in the R context, where each function is a tool designed to do a particular thing. You need the correct type of object to pass to those functions so that they're able to change things that you're then able to use downstream for your particular analysis. So we're going to be exploring this in the context of today. So far, we've only worked with very simple object types. Like last week, we introduced vectors lists that contain all character values. In the case of flowCore, looking at FTSE, PE, APC, we also had lists that were composed of numeric values as well as logical values. So in the context of what we're doing today, we're looking at much more complicated objects, which are going to be the flowFrames. And then we're going to also work through some of the intermediate kinds of object types in the process of going and exploring through our FCS file, just so we're getting a little bit more familiar with how things are working within R. So a little bit of housekeeping. At this point, we are touching our material that was covered during the first week of the course, namely installing R packages, as well as last week when we were talking about file paths. I know some of you don't have as much flow cytometry experience when you signed up, so if you're trying to get additional context about the flow cytometry side of things, I still recommend the University of Chicago flow channel on YouTube, especially their Flow Basics tutorial, just to provide additional context as far as what terminology means and why are we trying to do a particular thing. Now, I want you guys to focus as far as what we're doing today. So if at any point throughout today you go, I have no idea what's going on, please pause, just take a break and circle back later in the day. So our goal for today is not to have you memorize how to quickly access the 100 plus archaic keywords found within an FCS file. That is not the main goal for today. The main goal for today is to showcase kind of what we'll do as far as trying to figure out how an object type works. We're doing an exploration workflow. So don't force yourself, don't power through. If you need to circle back when you're in the actual exploring mindset, that's perfectly okay. The main thing as far as what I would like you guys to think as we're getting started for today is consider what kinds of informations that may be within an FCS file that you would like to be able to retrieve for your own particular analysis. And then as we explore the different pieces and components of a flowFrame, just kind of see how these various paths we navigate eventually lead you to that information that you're looking for. And same thing as housekeeping, as we do every week. There's new additional data sets that have been uploaded to GitHub on the courses Cytometry and R project folder. So if you have already forked your own version of Cytometry and R, just go ahead and resync that folder just to bring in all those new changes and all that new data to your local GitHub account. Once you have done that, just remember, kind of like what we did last week for week 2, you open up Positron and you're just going to pull in that data to your local computer, making it available. And once you have it on your local computer, you're going to transfer the data to a different project folder. If you're continuing what we did last week, you call a new folder week 3. Just make it somewhere that you're actually able to edit without affecting bringing in new data sets. And then once you have everything set up for your actual starting to work on your code, just make an initial commit and then push all those changes you made to your own project folder back to GitHub so that it's archived. Worst case scenario if something happens to your computer. And with that, let's begin the material for today. So, kind of similar to what we were doing last week, if you have set up a new GitHub repository on your computer as far as a project folder, and say you named it week 3, first thing we need to do is we need to tell our computer where to find those FCS files that we have just transferred over. So if you have retained the same kind of project organization as what we were doing last week, your file path might look like something like this. So if our FCS files are present within our data subfolder of our week 3 project, we're going to provide a path using the file.path function, just telling it which folder to look in, and we're going to assign it to an object we're going to call path to data folder. Once we have this file path specified, we can then go back in and actually find our FCS files using the list.files function we were using last week, which is basically telling the list.files function, hey, go search this particular path, look for anything that has the pattern .fcs, and just give us back that list. And we're setting that full.names argument equal to true, so it also includes the correct file path to find those FCS files. So if we do this and we assign it to the object that's called FCS underscore files, we can see currently within that data folder for this particular walkthrough, there's only a single FCS file present. It's within data. It's one of the cell counts FCS files we worked with last week. So now that we have identified the FCS file that we're interested in and we have the actual full file path, we're able to work with it in R. So remembering what we did last week, if we didn't have the full file path specified, it would look something like this, where you're just getting back the file name. But your computer would not know where to find this particular file relevant to the actual working directory in which we were present. Similarly, if we had set, if we didn't want to retrieve the full file path to that particular file, but we're just trying to get back the actual FCS file name, we could use the base name function, which we introduced last week, which will basically chop off the data / portion of that file path just to retrieve actually the FCS file. So today, we're going to be introducing a new R package that we're going to be working with, specifically the flowCore package. So flowCore is the oldest package for flow cytometry that's available via the Bioconductor project. It has been on Bioconductor for 19 years now, and it's one of the most widely downloaded packages as far as the flow cytometry side. So this particular graph doesn't show very well on my slides right now. It's being clipped at the bottom, but if you look at it on the website, you'll see these are all 69 packages for flow cytometry that are currently available on the Bioconductor project. They're sorted based on the year they were actually originally set up on Bioconductor, and then you just see the progression over time, and you'll find flowCore is very much at the very bottom of the list. If you're actually looking at it in terms of number of downloads, every time Bioconductor updates to a new cycle, everything has to re-download the new version of the package. You'll end up seeing that flowCore is actually the oldest package, so it's on the x-axis, and you can see it's over here on the very far right. Now, this is a type of plot. It's called a plotly plot. You'll see these sporadically. They're interactive. So if you're just interested in particular packages, all you would need to do is double-click, and you could see where they are on the actual chart itself. So some of the packages we're going to be working with in the next couple of weeks are the flowCore package, the flow workspace package. Let me double-click once. And then later on in the course, we're going to be working with flowsum and cytoml. So you can kind of see, you can make this a little bit more interactive, and you can see the difference as far as downloads and the years that are present on Bioconductor. So across the board, because flowCore is used by so many different packages, it is the one that gets downloaded the most. And this is kind of reminiscent of one of those XKCD packages. So namely, the flowCore package, as well as many of the other cytometry packages, are maintained by Mike Jung. And it's very similar to this particular comic that always strikes me, where all the bioconductor flow cytometry package infrastructure are projects that either Mike or his associates are maintaining, thanklessly maintaining since about around 2007 or so. So a lot of what we do right now in R is thanks to their work. So as we do with every single R package, we have installed it. It's now available. In this case, we installed it from the bioconductor project, so it's just bioc manager loaded to the library and then install. Once you have it installed, we need to still attach it to our local environment so that we're able to use the functions within the package. And this is where we need to go and use the library call just to make sure it's active for us. At which point, we then need to go and use what's known as the read.fcs function. So if you're trying to remember how do I access the documentation, this is where I would prompt you. And just touching down the drop-down arrow, you would remember we can either throw the little question mark in front of the function name, which would get us the actual information about that particular function. Or if you're within positron and you're working within a code chunk, you can just hover over the function name and the help documentation should pull up. So read.fcs will take in the actual file path to a particular FCS file, and it will read that into the R environment, making all the contents available for us to use. So in this case, we only have one FCS file, but if you were following along at home and you just pointed it at your entire folder, you need to specify a single file that's going to be read in by the read.fcs function. So we can basically subset this big list of files and their file path locations by using those little square brackets and just giving it index location. So in this case, I'm saying of the object we have that's FCS files, just grab the very first value and assign that to the new object we're going to call first file at that point. And as you see, when we print first file, we see the location of our particular FCS file of interest. So at this point, we are going to be passing that file path to read.fcs so it can be read in. And we're passing it specifically to the argument that's known as file name. So if you're going to go set this up in your console window right now, it's going to look something like read.fcs file name argument is equal to first file, which is the file path to our actual FCS file of interest. And the main thing I want you to emphasize is this is just reading in the simplest version, but if you encounter code in the wild, doesn't matter who's working on the R code, you'll often see these two additional arguments present. Transformation is equal to false, and truncate max range is also set false as in terms of arguments. The reason for this is if you just read it in, kind of like what we just did now, it's just going to automatically transform and automatically truncate the range of your particular FCS file, which may not be what you want to do if you're working with spectral flow cytometry files or you're working with like Cytof files. So if you're working with any of these variants, just make sure to set those arguments initially set to false so that if you're changing any transformation, etc., you're the one deciding what you want to change, not whatever arbitrary change is happening within the package level. So if you do this and you then hit enter on that line of code, you'll see this particular object is read in, and this particular output gets printed to your console window. Basically, we can see the output of this function is showing you it's a flowFrame object, where then it gives the name of the particular file. It gives you a little bit of details about cells and observables. We'll talk about what those are in just a second. And then you can see there's like multiple columns scrolling down before we see a certain line telling us about the number of keywords available in the description slot. So what we have just encountered here is what's known as a flowFrame object. So the description is basically what I just walked through just now. We see that there's 100 cells, 61 observables. When we are thinking about what we just read into the particular environment, this particular SCS file happens to be a raw spectral flow cytometry file. So those 61 detectors kind of give you the cue that this is likely corresponding to the individual detectors available on a 4-laser Cytic Aurora. In my case, I had downsampled the file, so the 100 mention of cells is likely just the actual 100 cells that are present in the particular file. And then, just like we saw, if we look into the actual columns, we can see the detectors on a Cytic Aurora are going to be present. If you're using different instrument manufacturer, you would see either if you're the other corresponding detector names in the case of a raw spectral flow cytometry file. If you had already a mix, this would be instead the fluorophores. Similarly, would be the case for a conventional flow cytometry file or a mass cytometry file. And then at the very bottom, we see keywords, and we just remember there's oftentimes keywords associated with the FCS file. In this case, it seems we have a lot of keywords that are potentially at play within this particular format. So at this point, let's just think whole picture. So we have loaded in an FCS file into R, and now we have it within an object that we can actually interact with. So in this case, we need to try to figure out what kind of object this is, what the bits and pieces are, and then if we have a goal of we want to retrieve the MFI data, or I want to see if my user ran this particular file at low, medium, or high acquisition speed, how do I go and figure out where within this particular object is this particular information or this particular data that I may want? So the first thing we should do is we learned a couple type functions last week, str and class. This could provide us additional cues, additional information as far as what we are working with as far as a particular object type. So if we're using the analogy as far as a toolbox, we had just found this new tool. It's called a flowFrame, but we don't actually know how it interacts with a particular function. So we just kind of need to poke and prod and try to figure out how exactly does it work. So to be able to use these type functions that we learned last week, we need to actually read this output to a particular object. So let's go ahead and save this to the new object flowFrame. So then we're able to use the actual functions as far as figuring out what kind of type of object this is downstream. So once we have done this, we can basically come back in and see we have run that line of code. There's now a new object within our environment. It's known as flowFrame, and you can see there's a little bit extra more information. We see a line that says something along the lines of S4 class flowFrame, square brackets, package flowCore with tree slots, and then it gives us the flowFrame. So this is the advantage of being in Positron. You can just look at the right secondary sidebar and just get some additional information, additional context without having to run any additional lines of code. So at this point, let's go ahead and tackle back to those type determining functions we were practicing with last week. So if we run that particular object flowFrame inside of the class function, you see it's retrieving some of that same information. We see the type of this class of this object is a flowFrame, and this is specified within the flowCore package. And then at this point, we're basically start trying to figure out what's going on. So based on that information we saw on the secondary sidebar, we can also see it's an S4 class flowFrame package flowCore with tree slots. So what a flowFrame is a particular type of object that's being defined within the flowCore package. It's used to actually contain the data that's being read in from your individual FCS files in a format that R can interact with relatively easy, and then retrieve particular sets of information, whether it's the metadata, whether it's the parameters, whether it's the actual MFI data for your particular file question. So as we are, however, first looking at this particular object appear within our right secondary sidebar, a perfectly valid first reaction is, how should I know what any of these words mean? So this is the initial discomfort we all face when we're working with a new object type class in R. It's not immediately intuitive. It's not immediately knowable. You could maybe search the help documentation and it might help, it might not. So what I find is the best way of trying to tackle these unknowns is kind of do a little bit of an object exploration and just try to break it down into the individual components until you have a good idea of what the different pieces within these more complicated objects are. So if we're thinking of a flowFrame as a type of an object, it's going to be one of those more complicated object types. So it's not going to be it's a nail or it's a screw. It's going to be more it's a cell counter that's on your bench, or it's going to be a vortex. It's going to be a little bit more complicated of a tool that we can use within our particular application for a given day. So the good thing is, if you're working within Positron and you have created that object, you can always click on these little drop-down arrows, and it will start showing you some additional information about the object. So in this case, if we drop down the arrow for flowFrame, we can see 3 new lines appear. We see one that says Exverse, that as you quickly skim, shows up as a matrix object. We see it has a particular row that says parameters, which is mentioning some other nebulous termed object annotated data frame that just leaves you equally confused, but then you can see it has 4 slots. And then you see something that says description, which at least as you scroll through that line kind of looks like some of those keywords you might have seen if you had opened up a commercial software and looked at the keywords as far as your particular FCS file. So at this point, as far as just trying to build context of you're trying to do an exploration, trying to figure out what's going on, we know this particular line up here at flowFrame said 3 slots. We got 3 additional lines appearing when we did the drop-down arrow. So these tree slots must be referring to expers, parameters, and the description. So at this point, we're getting a little bit of cues, and then we are like starting to work our way inside the object and try to figure out a little bit more as far as the bits and pieces go. So assuming that our guess as far as the slots is correct, let's go ahead and look through the very first object. And just to remind everybody, flowFrame objects are basically what's known as an S4 object type. S4 objects are very common for bioconductor packages. The reasons behind this we'll get through throughout the course. The main thing is it allows your data to travel with the metadata, and you're not breaking the two apart and having to move two separate pieces. That's the smallest explanation as far as like why the bioconductor project likes their S4 object types. Versus if you look at some of the tidyverse packages, they may use a different format, which is called as tree. The focus as far as like the difference of those two is not anything you're going to be concerned about for the vast majority of this course. All right, so at this point we have broken into flowFrame. We have tinkered around and found there's tree slots. These tree slots are expers, parameters, and description. Let's do this sequentially, and let's just take a look quickly as far as what we're able to see with expers. So if we're looking at that right secondary sidebar, we can see that in the middle it did say matrix. It also listed saying 100 rows, 61 columns. We can recall when we did the read.fcs function a little bit earlier in the day, we had something similar as far as what was appearing at the very top. So at this point, this is our first kind of clue that what we're seeing in this expert slot is likely going to be the MFI data for the individual cells for each of the detectors or each of the individual flowCores that are present for a particular FCS file. So let's pursue this and see if this is actually the case. So if you're working within positron and you see this little kind of grid object on the side, this basically stands for that particular object is a table kind of object, either a matrix or a data frame, which means if you come over here and click on this little grid icon, it's actually going to be able to show you what the overall data is when it pops up in the editor window. So at this point, I would go ahead and slide over to the far right and click on that little grid and see what happens. As you do this, it's going to pop up the actual underlying data set, and it's going to open up in your editor window, which is at the top center of your screen, kind of like the same section as where you'd be actually writing code if you were clicked over here on the .qmd file. And in this case, you can kind of see that your suspicion is kind of correct. So the individual columns seem to be corresponding to the individual detectors for a raw FCS file. If we scrolled all the way down to the very bottom, we'd see there's up to 100 rows, which corresponds to the number of downsample cells I had present for my particular file. And then the useful thing about positron is it does give you a little kind of summary section right here on the left side of the screen, as far as like what the particular values are, if there's any missing data. This is one of like the general overviews of what you're able to see. So at this point, we have explored down within flowFrame object, and then we looked at the expert slot of that flowFrame object, but we're not able to work with this directly in R yet. So if we're actually like trying to grab like what were the UV16 detector values for all my 100 cells, we need to have this in an actual object within our R environment that we're able to manipulate and change accordingly if we're like trying to plot the underlying data. So the way you get in and extract out the bits of information within a flowFrame object is you need to access the individual slots and then designate to that particular object outside. And the way you do this is you're using what's known as an accessor. In this case, you're using the little @ symbol, which basically corresponds to, hey, check within this particular slot, retrieve the data that's present in there. So if we set this up as far as like trying to extract the data, so we now have it in our R environment and we're then able to use it, we're basically specifying for the flowFrame, which we had saved under the flowFrame object variable, access the expert slot and retrieve all the underlying data, and then assign that to this new object, MFI_matrix, so that we're able to do work with it downstream. Alternatively, bioconductor packages often have helper functions that will do that same kind of steps, but without having to add all those extra @ symbols. So if you remembered it off the bat, you could remember that the helper function in this case to get at the expers slot of a particular flowFrame object is going to be expers. So as you can see, we could just run the expers function, and then it does all the handling as far as extracting out the data that's located within that particular slot. So at this point, remember, we have 100 different rows. So if we just printed all those 100 rows individually for all 62 detectors, it's going to take up a lot of space within our console. We'll have to scroll up quite a bit. So we may want to actually subset how many number of rows we're particularly showing at a given point in time. So the way you do that in R is there's the function called head, and basically you give it the matrix style object that you have. In this case, we had assigned that to the MFI matrix object variable name, and then you just tell it how many rows you want to actually see. So in this case, I set it for 5. So you see, we can see the first 5 rows for the first set of detectors. And then as you look down your console window, it'll give you the next set of detectors, the same 5 rows, their respective values. And it continues all the way down until we hit the R8 detector in the Cytek Aurora setting. So this is a way of getting an abbreviated view without completely overwhelming your console with lines and lines of text that are quickly scrolling by, and you then end up not being able to see what you ran before. The alternate, well, this is particularly good and useful in the context of a small laptop screen. But remembering back to what we had just seen when we had opened up the matrix within the editor window, we saw there's a lot of different column names. So if we actually wanted to retrieve those column names so that we're able to work with them, or subset, we want just the R8 detector or the forward scatter or particular detector name, how do we get these column names out so we're able to use them within R? So the way we do that is using the column names function. And basically, we're just assigning this little matrix object we have created, we're running it through the column names function, and it's going to retrieve out the actual column names of our particular interest. So when we do this, we see it did retrieve the column names correctly, but it's also giving us this other weird printout within the same view with the console. We see it's like a $P1N, $P2N, etc., etc. So this doesn't quite make sense, but we did get some of the actual column name information that we wanted. So at this point, this is our first cue that this is not exactly the same kind of vector kind of list that we were working with last week when we were assigning floors or antibodies in our panel, etc., etc. So we should probably at this point look and try to see for this new object we have created, column names, what kind of type of object is this, and what can we do as far as figuring out a little bit more about it. So in this case, as we continue down, let's use the str and the class functions that we had worked with last week, but just use it on column names to try to see why it's giving us that weird printout as far as $P certain number n as far as the location. So when we run the str function on column names, we can see, similar to what we had last week, it's showing up as character values. It tells us there's up to 61 values present within that list, going from time, UV1, UV2, essentially corresponding to those original column names we saw within that matrix. But we also see it shows up with named directly in front of the character. And then if you look, there's a second line which says attributes names, and then once again, it's also showing up as characters ranging from 1 to 61. So what it looks to be, at least at first glance, is for each of our individual column names, there's an associated name with those, which is corresponding to those P1N, P2N, P3N, P4N. So we've gathered this from context, but we actually don't know what's going on here. So this is one of those areas, if you're doing this exploration on your own, there's going to be this little bit of uncertainty. We don't have immediate context as far as what's going on. So let's just put this aside for now, and we'll circle back and try to figure out what's going on with this in just a couple minutes. But let's go ahead and also check that second function we have in our toolbox, the class function, and see if it's going to provide additional information, kind of like what we saw for last week. However, in this case, if we ran it on class column names with the class function, it's just returning as character. So it's not providing any additional information that's useful to us in trying to figure out what this P1N, P2N, etc. are actually meaning. And this is kind of the main reason why, if you have multiple ways of doing something in R, it's often useful to just go ahead and check, because it does provide additional information. Because if we had run class as our first information, we would have never seen these extra named variables that are present, and we wouldn't know they exist until potentially we see an error later on down the line, or we accidentally grab the P1N, P2N, or something like that. So it's always good to check multiple ways you know of how to go about and do something. Now, in this case, we have these extra sets of names. It appears to be a named list of some form. So if we didn't want to keep the named list, but we wanted to keep just the column names, kind of like what we saw last week for the flowCore object, we could use the function that's the unnamed function, which is basically going to strip the names off of that particular list, and it's just going to leave us with the actual column names that we're interested in. So this is a way of getting rid of the names that we see present on that object type. All right, so at this point, we are taking our attention a little bit back to that right secondary sidebar. We kind of already perused this little matrix option when we clicked on it, but there's still a little drop-down menu, so we're trying to be a little thorough. Let's go ahead and click and see what happens. And in this case, what we see, it quickly drops down another 61 set of lines, and it's not particularly user-friendly or visually friendly as far as at first glance. So you can see everything within the first values column. It's showing up as square brackets, comma 1, comma 2, comma 3, increasing numbers as you descend. And then you see values that are present within the actual row. If you actually were trying to match what these are, you would see eventually it does seem to correspond to the actual values for each column that are present for a particular row, but definitely not friendly, definitely not something I would want to be interacting with directly. So what is actually going on as far as this square bracket, comma 1, square bracket, comma 2? What does any of this mean? So within base R, which is basically just what you get when you install the R software, you haven't installed any additional packages. The column order is defined by placing the particular column index, like is it the first column, is it the second column, after a comma within that square brackets. So for example, if we wanted to grab the very first column of our particular matrix-like object, you do I want square brackets, comma 1, which is going to grab that very first column and all the values associated with it. Vice versa, if you wanted the very last column of our particular object type, we could do comma 61, which is going to grab the 61st column in our MFI matrix object, and it's going to return those values to us. So this is the base R notation of how you go about getting an actual column. Now, what would happen if you specified a column index number that doesn't exist? Well, let's quickly check. So this one only had 62 columns. If we tell it, grab me the 350th column, it's going to give you this error message, which you'll encounter frequently enough that's useful to get the key of oh, this means it must not have had 350 columns, where it tells you subscripts is out of bound. So if our columns are being specified by placing the index number after the comma, how would we get the actual row? So if instead of wanting columns, we were trying to retrieve a particular row. So in row, in base R, it's actually the number that would appear before the comma. So if I wanted the first row, I would place that first index number before the comma. If I wanted the last row, which would be, I have 100 cells for this downsample, I'd put 100 comma within those square brackets to get back the 100th row. And we're not going to cover it very much today, but if we wanted a particular value, like the first cell's value for the UV1 detector, if we knew the UV1 detector was the second column, combining both the row notation and the column notation, we could get back individual values for our particular matrix as far as what we have. But this is not the focus of today. We're just slicing and dicing our way through an FCS file. So this is there for context, and we will revisit it if we need it later on in the course. So at this point, it doesn't look like there's very much left in the Xverse. We saw it was very unfriendly when we looked at it within the right primary sidebar, right secondary sidebar. So at that point, let's just continue on and look at the next parameter slot, which is parameters. Now, if you remember back to what we saw for the right secondary sidebar, it looked particularly unfriendly in terms of that initial name. It showed up as an annotated data frame object, which is defined by the biobase package, and then it has 4 slots. So it's kind of similar to what we saw when we first dived into the flowFrame. So at this point, we have carved our way this far into the heart of an FCS file. We see that this next object is also going to be complicated. Our first initial reaction is, do we really want to mess with this? But at this point, we're not about to call it quits. So I urge you all to charge forward. Go ahead and click on that little drop-down arrow. Let's see what's inside this other complicated object that's within our initial complicated object. And when we do so, we have braved the way and we have seen it. We can see that this drops down and those 4 slots are now revealed. We have a var metadata column, we have a data column, we have a dim labels, and we have a class version corresponding to these 4 slots within this particular object. And fortunately for us, because we have just navigated through this in the last one, we see that 2 of these objects look like little table objects, so they're going to be able to open up in the editor window, which is going to be much simpler for us to quickly be able to look at. The other 2 look a little bit more nebulous and a little bit more hesitant as far as what they may be doing. So let's at least start tackling the very first one we encounter. So if we look at this little var metadata slot, remembering we're trying to find different bits of information that may be useful to us. In our case, we already found the MFI data, so we don't need to search for that. But if we're trying to find a particular variables as far as keywords or descriptions that are like, lets us know how was this file acquired? Was it acquired at low speed, high speed? What was the voltage for a particular day? That kind of set of information. We don't actually know those variables yet, so we're still trying to figure out where they are. So if we look at var metadata and we click on the little grid within the positron window, it's going to open up within our editor. And you can kind of see for var metadata, it's relatively simple. There's a single column object. It tells you name, description, range, and a couple other things on the actual row names themselves. You can see the column is called label description, and then it gives you particular values, name of parameter, description of parameter, etc., etc. The main thing I'll point out for here is if you're looking within positron, you can see this object is a data.frame object, which is also very similar to what we see for a matrix object. The difference as far as data frames is they can also include things that are not necessarily numeric values. They can do a lot more with characters. They're a little bit more multifunctional, which is why we'll encounter them kind of frequently within R. So it's just a good idea of like to know what a data frame object is. It's one of those intermediate type of objects, somewhere between a simple list and a more complicated like flowFrame kind of object for us. So in this case, we kind of maxed out as far as what we're able to see. There's not very much else there, so that seems a little bit simple. But we can also remember the outputs don't look exactly like what we saw for the read.fcs output, but they kind of look a little familiar. There's like name, description, range, min range, max range. Those did correspond a little bit in what we're actually seeing for those associated values, but not quite what we wanted. So at this point, we're kind of getting a suspicion that that next matrix might actually be containing these particular values that we saw during that initial output. So let's go ahead and click on the data slot, and sure enough, it will open up in our editor window, and we see that, yeah, those columns that we saw from that initial read.fcs function, these are now appearing. We see name, description, range, main range, max range, and then we see the detectors going down. We see this little description slot, which is currently empty, which is the case if this is a raw spectral flow cytometry file. If we had a mix, and instead of seeing individual detectors, we had the fluorophores. Same thing if you were in a conventional instrument or a mass cytometry file. This description file would actually have the markers of our particular interest that we had assigned at the instrument side. So we have a little bit more information at this point, and if this was what we were trying to grab, we'd have the data that we wanted. But this is not quite what we wanted. However, if you want to work with what this is present in this slot in R, we're going to need to be able to get it out of the parameters and then out of flowFrame so that then we can have this little data frame object present within our R environment, so we're able to manipulate it, change it, edit it as we need to. So to actually go about and extract that information, what we're basically is going to do is kind of similar to what we already did. We need to go into the flowFrame object, and then using the accessor at, we're going to go and retrieve the parameter slot that's present within. And because this is also a complicated object, we're going to have to do that second accessor to then go and grab the data slot itself. And we're assigning data within parameters within flowFrame to this new object within our R environment that we can actually edit and work with. So in this case, if we actually print the parameter data, we now have these particular values that we're able to work with and able to work around. And at this point, we're still seeing this little $P1, $P2, but at this point, between the expers return and both this return, we're kind of seeing they're at least corresponding to the individual detectors each and every time, which is kind of like a little bit of a context cue that we still don't know exactly what these are doing, but they seem to be pointing at these particular detectors in a consistent manner. So it might be something internal as far as like the actual organization of our flowFrame object. And just like we did with expers, there's a more direct way of accessing data within your parameters slots. This is the helper function known as parameters. So if we're trying to get at the data, basically we're getting the parameter slot of flowFrame, and then we just need to add the accessor slot outside to be able to grab parameters data slot. I realize this is a little confusing and tongue twister-ish as we go in and try to grab a slot of a slot as we go into an object. Now, if we actually are checking to see what kind of type this particular object we retrieve, we could run str, and sure enough, it comes back as the data frame that we saw a little bit earlier when we looked at the right secondary sidebar. And you can kind of see there's a little bit of names associated. So we have $signs going down corresponding to each of those columns. We can see what kind of column those particular ones are. We can see this one is a named character, name character as well, and then numerics as we go down. So we're getting a little bit more information about these individual columns and the values that are contained within. And in this case, you'll notice when we're trying to access those particular values, it's showing up as little dollar signs next to them, not as a little @ sign that we had when we were working with slots. So if we were actually trying to subset out a particular column, how would we go about trying to get, let's say, the description or the range? So when we're working with a flowFrame object, if we're trying to grab parameters or we're trying to grab expers, or in this case, we try to grab data, we're just adding those @ symbols on the outside. But if we're trying to work with this particular one we just set up where we extracted out the data frame, if we start typing it out and write that little @ symbol, nothing is going to happen, nothing is going to be suggested at this point in time. The reason for this is data frames don't use the @ when you're trying to access particular columns. If you're trying to subset out a particular column, however, you could use the little dollar sign, which is going to serve as the accessor function to getting at a particular column. So if we started to type this out, parameter data, which is where we save the data to, and then we add the little dollar sign, it's going to pop up a list of suggestions corresponding to those individual column names that are present within our data frame itself. So this is how we'd be able to go in and dive and grab a particular column. As you become more familiar with R, the remembering, is this a situation we need to use @ or a situation we need to use the dollar sign, this will become more intuitive as you start connecting the bits and pieces as far as what type of object am I working with? Is this one of those complicated ones where it has individual slots, or is it more simple like a matrix or a data frame where you can just use the dollar sign to access a particular column name? And similarly to what we saw with matrix, you can still use the base R terminology and be able to access a particular column. So even though it's a data frame, if we gave it the square brackets, comma 1, it would grab us the first column within that data frame itself. And yeah, this was a description I gave a little bit earlier. We saw that under name, it was giving us the particular detectors in our case. If it had been a conventional file or a mixed spectral flow cytometry file, it would have given us the fluorophores. Description was empty for this particular file, but that's where we could see the actual marker or antigen we assigned to that particular detector or fluorophore. The last three, range, min range, and max range, we're not going to go into today. If you actually start tinkering and altering them, they kind of will throw commercial softwares off as far as how much they zoom in. So at least as far as when you're looking at the commercial software side, they do have importance. If you really wanted the actual details, the flow cytometry standard, which details all the little components of an FCS file, is where you would go for the reference. Now, at this point, we have looked through the var metadata and the data slot within parameters. So we still have those last two that looked a little bit more ominous and didn't look immediately interpretable. So let's steel ourselves. Let's go check the dim labels. We click on it, anticipating another huge amount of information. But fortunately for us, it just returns two labels: row names, column names, no additional information available. So cool, we don't have to actually deep dive and figure out what's going on with this particular slot. Same thing, when we check class version, we steel ourselves, we click on it, and then it just gives us back annotated data frame 1.10. So probably the version of this type of object. So both of these slots are not stuff that we actually need to know for our particular purpose. It's just extra information about how R is storing a particular object. So probably useful to the developer, not interested to us as people who are just trying to do our analysis. So at that point, we can say, okay, we're good. There's no additional information to be retrieved from the parameter slot. At which point we can continue on. And that very last slot that we need to look at, having looked at expers and having looked at parameters, is description. So at this point, if you're still trying to find that metadata as far as being able to pinpoint what was the voltage for that particular detector today, or were your users abusing the instrument and acquiring too high of a concentration in too low of a volume at too high of a speed, this is our bet of where likely our data is somewhere present, and we need to find it at that point. So at this point, if we click on the description slot, it's going to open a lot of rows immediately. And this kind of makes sense because we can see at the very top, it's a large list that has 599 objects present. Just looking at it initially, we can see, okay, there's cytometer, that stands for the Aurora, so that must be the instrument we acquired it on. Date is probably when that particular FCS file was acquired, but it's quite a heavy list of 599. So that's quite a bit to just scroll through and try to remember which each of these is individually. So let's try to instead extract out the information that's present, i.e. grab this list and assign it to a particular object in R, that we're able to work with and get actual information out of. So just like we did for all the other slots within flowFrames, we're going to need to use that accessor to then grab all the contents of the description, and we're going to assign it out to what our variable is going to be, the description list. So when we do so, it grabs the entire list, all 599 keywords of it, and it's there. In this case, it's still a little bit too much to work with. I wouldn't recommend working with it all as a single output. If you printed this to your actual display in your console window, it would just completely overwhelm everything. So it's not a good way of being able to work with it directly. However, we can still use those functions we've been using throughout today to kind of make it a little bit more manageable and tackle it in a piecemeal function. So if we try the head function, it works. We can get back the first 5 elements, which is what we were seeing already a little bit on the positron side. This is useful, but we could also consider using the position indexing so we can grab certain stretches of keywords. So if we're thinking of our list, description list, we could grab the first 10 items. So going from 1 to 10 when we include the low colon in the middle, and it'll grab the very first 10 keywords. If we wanted to grab the last 500 to 600 keywords, we just put 500 colon 600, and it would grab the 500th object through the 600 object values that are present within the description list. So at this point, just like we had for exprs and parameters, there's also the bioconductor helper function, which would help you avoid having to use the accessor when you're trying to grab something. In this case, it's the keyword function. Of all the 3, keyword and exprs are going to be the ones that you most likely are going to encounter throughout the course, just because those tend to be information that we actually are interested in and are actually trying to retrieve. Parameters is not one we encounter very often in actual practice. So kind of same thing. You could be able to extract that same keyword list if you are trying to do it. And let's just go ahead and double check what we see, because at this point we have checked the previous 2 types and we saw that exprs retrieved as a matrix type object. For the parameters data slot, it came back as a data frame type object. We saw for this one that it was a list, but let's just double check to make sure there's nothing finicky happening as far as the type, kind of like what we saw for a named vector list earlier. So when we run a class on description list, it comes back as an actual list as the type of object that we're working with. Now, this is in contrast to what we were encountering last week when we set up flowFrame, where when we actually ran class on it, it returned as character. So the reason for this is what we were working with last week, which we're collectively calling a list. At that point, is not actually a pure list. It's what's known as a vector, which is also known as an atomic list. And these kind of list-like objects will contain things that are only one particular type of object. So they're all character values, or they're all numeric values, or they're all logical values. So if we're trying to repeat what we did last week, we could generate this vector style list for BV421, FITSI, PE, APC, and we're assigning it to the object flowFrame. And when we call class, it's not returning a list, it's returning an atomic class of character at that point. Same thing if we did the same sequence of bipanel antibody counts, it'd come back as numeric. And instead, if we did a logical sequence, it's going to come back as logical itself. So if we compare it to that last return where it's showing up as a list, these are what we know as vectors or atomic lists, in this particular case corresponding to the actual value type that's present. So how would we actually get an actual list, kind of matching what we just saw for that type? So the way you could create an actual list is using the list function instead of the seek for the concatenate, which is what we're doing for vectors. So in this case, lists in general are a little bit more gregarious. So they can contain things that are numerics, they can contain things that are logicals, they can contain lists within the list, they can contain matrices, they can contain data frames. A list can pretty much, you can incorporate anything that you want within individual positions in that list. So in this case, I'm basically creating a list that contains our particular vectors we have just created. So when I create my list of vectors, you see it appears as a list when we run structure. And you can see the first object in the list is the character vector BV421, FITSI, PE, APC, kind of corresponding to our flowFrame object. And you get the same kind of structural information out when it comes to numerics and to logicals. So at this point, you can kind of remember back when we just ran the structure on the entire list. It looks kind of similar to what we just encountered, where we have character, numeric, logical, and our particular values. we have these little dollar signs on the side. But if we actually remember back to what we saw just now, there's also this middle stretch where we have these individual keywords present. So we have begin analysis, begin data, etc., etc. So this is not quite matching with what we're seeing. So what's actually going on in this case? So how do we actually get these names to appear within our particular list if that's what we're trying to do? So the way you would do this is basically within a list, you can create a name for the particular thing you're adding into your list. So if we wanted to have like this have a name, we could say fluorophores named is equal to the vector fluorophores, panel antibody counts name is equal to our panel antibody counts, etc., etc. In this case, we get a readout that looks much more similar to what we saw for the description list, where we have the dollar sign, the particular name of that list object, and then the actual things present within that object being shown on the side, as well as the structural information. So why would that actually be useful? So if you think about it in context of our description list right now, we have 400 to 600 keywords present, and we don't want to have to remember, is cytometer keyword the 5th index, the 42nd index, the 399th index? We don't want to have to mess with like figuring out what index position on the list that particular keyword of interest is. However, lists are very similar to data frames, where if you include the little dollar sign accessor symbol, you can just start writing out the particular name of a keyword, and it's going to immediately pull that up in the suggestions, and you're going to be able to quickly retrieve the data. So that's the advantage of having an actual named list, where you're able to quickly just identify what particular keyword of interest you actually want to work with. Of course, you could still use the index position if you knew the location of it, but it's just a little bit less friendly as far as the day-to-day operation goes. So at this point, you may be remembering back when we started the day, we did read.fcs, and it mentioned something about 599 keywords being present within that description slot. And I know for a few of you, you may be having the fear of, oh no, this is where David starts going through all 599 keywords, and we're going to be here at least through tomorrow. Don't worry, I don't want to do that. I definitely don't want to do that to any of you. I want to get more of a big, broad overview of like the types of keywords for an FCS file that are present, just so if they do correspond to something that you're trying to retrieve later on in the future, you know, hey, this is likely going to be within those keyword slots. I should go and check to see if this value was actually recorded for my individual FCS file. So within the world of the keyword madness, we're just taking a big bird's eye view of the contents of this keyword list that are present for the FCS file in general. So if we were trying to subset down this list, we could just say by positions, which kind of breaks it into little chunks. And if you see, we assign this to this variable we're not calling subset, and we can just scroll down and see all the little keywords that are present for this one. So the bird's eye view of what's present, the first initial sets of keywords within an FCS file are very much the early metadata. So things like what was the start time of the FCS file would be contained within an actual keyword that's called $BTIM. You'll notice when it comes to keywords, they're all showing up as characters if you're looking at the structure of the list. But remember, dollar signs are one of those special characters. Your computer will try to interpret these as code if you provided it. So just like we saw, we could do description list, dollar sign, and it's expecting you to access a particular location. So if we didn't have quotation marks or little tick marks around it, your computer would be trying to run this as code. So especially within this early metadata portion, all the actual keywords themselves are saved as dollar signs at the very start. So in this case, if you're trying to write out the name of a particular keyword, you're going to need to include those little tick marks just to not run foul with the computer mistaking something as a line of code. Same thing, we saw this a little bit earlier. You can retrieve what the cytometer your FCS file was acquired on. In this case, this was the Cytec Aurora. You could get the serial number if your field service engineer is trying to ask you which instrument is currently having the issue. We could get the acquisition date for the FCS file. There's a couple additional ones like start time, end time, the file name itself, kind of like what we've been retrieving. So if these were like bits of information from an FCS file that you actually needed, you'd be able to retrieve it. And then who actually ran the sample. In this case, this is one of the samples I had acquired myself. After this little early metadata stretch within the keywords, we get the actual detector values. And at least in the context of a spectral flow cytometry file, the vast majority of the keywords correspond to these. And if you scroll down, they just don't look initially very understandable. There's a bunch of those same kind of symbols we were seeing elsewhere popping up, like P a certain number, N, P a certain number, E, etc., etc. So especially initially, this does not look very friendly. But if you stared at it long enough and started like working out what kind of pattern may be present, you'll see that the numbers change as far as which detector is being designated, but it's always coming up $P, certain number B, followed by an E, followed by an E, followed by an R, etc., etc. So that's still not understandable, like what do these particular keywords mean, but at least they're following some kind of pattern, so maybe we have some hope of being able to decipher what's going on. So as we actually look at it in the context of, let's say, the 7 detector, we see that B comes back as 32. We see N, at least, it seems to be corresponding to the name. It's showing up as UB6A. We see that this is raw fluorescence. Considering this is a raw FCS file, this kind of makes sense as far as a type associated with the UV6 detector. And there's a bunch of other numbers that don't immediately make sense. So this is one of those situations you're not going to get additional information from this FCS file to explain what's present. But if we did remember, we have that flow cytometry standard documentation. If you went back and were actually curious enough to like dive through and read through it all, if you had that time to kill, you could come back and figure out like what these actual particular values correspond to. So in this case, for B, it stands for number of bits. I'm not a computer scientist. This doesn't immediately make obvious sense. I kind of vaguely understand what a bit is, but it doesn't seem to affect me on a daily basis, so I'm just going to skip over it. Same thing, if you're approaching it for the first time, you see that the E value stands for amplification type. But then when you see the actual value returned 0, 0, you're like, I still don't understand this. So that's one of those things you'd bookmark to go reopen the documentation, try to understand what's happening. It's not something we're immediately, obviously, understanding what's going on. Short names for parameter N makes a little bit more sense, and that's kind of like where we saw for UV6. So that one, like, okay, I understand what's going on for this one. Maybe I could have a use case for that one in the future. Range, you get these values back that are kind of similar to what we were seeing from the read.fcs file. We kind of have a vague idea of how a range works on a cytometer, so kind of have some context there, but not immediately obvious. Type, raw fluorescence, this was one we kind of understood, so we just continued. And then detector voltage for parameter N. So at least you know this particular value must be the voltage or the gain that was set for that instrument for this particular detector on that particular day. So when I first was exploring through this description and keyword list, there was not an immediate, very good, obvious value to this massive stretch of 300 different keywords in a row. But later on, I did find a quite useful use for these, especially in the context of these keywords providing the name of a particular detector and then the voltage of a particular detector on an individual day. So in the case of our core, we ended up building an automated instrument QC dashboard for all the instruments in our core. That includes the BD instruments, the Cytic Aurora instruments, the Amnis, the MaxQuant, just because all these individual files we acquire reference QC beads for every single day when we are trying to make sure the instrument is staying up in good condition. And every time we acquire these single FCS file of the QC beads, we're actually grabbing metadata about each of the individual detectors or channels, but we also are retrieving the gain or the voltage setting for that particular instrument on that particular day. So building out the dashboard, it kind of helps us as have a place where users can go back to and then check to see how the particular instrument did as far as QC for that particular day. But also, when we have that set of information, we know what the detector name is, and we know what the gain voltage for a particular file is on that particular day. That allows us to basically build Levy-Jennings plots for all our instruments, regardless if it's actually something that the individual instrument manufacturer offered. So that at that point, we just have to plot it longitudinally, and we're actually able to see what's the chain in gain, what's the chain in voltage for a particular instrument on a particular day. So in this case, for this particular instrument, I think this was our Aurora tree, we could see the gain start to spike on the violet laser, and we were able to like call our field service engineer to come out about a month in advance of when they actually started triggering the Cytic Aurora QC fails, because at that point we had a key of like, hey, this laser is starting to like burn out, the gain is constantly being ramped up. So this is one of those advantages of having like tinkered around and figuring out how can we extract out this little metadata about the detectors and about the actual voltages to be useful. And then if you're on the website itself, I did link back to the dashboard. So if you want to like see how our particular instruments are behaving on a particular day. It's in an automated fashion, and it updates around, I think it's like 11 o'clock every morning. So if you're thinking in terms of the voltage and the gains, we just went through a stretch that was very similar across the board for all the individual detectors of a particular instrument, but there is a little bit of variance as far as this particular pattern. So if you think of our particular columns in our FCS file, we have a few that are like forward scatter, side scatter. This still looks very similar to that same kind of pattern we saw for the actual flowCores or the actual detectors, but you just see the type has changed from raw fluorescence to forward scatter. And this is one of those things that, like if you're using FlowJo or FCS Express, it's used to kind of cue in as far as what kind of bi-exponential transformation or linear transformation needs to happen on an individual FCS file as you open it within the software. And then similar thing happens for time. Obviously, type has been changed to time, and you can see the range is different on time than compared to what it was for your forward scatter or your raw fluorescence channels. So at this point, the very first set of the keywords we have encountered for the first about 2/3 of all these different keywords. There was the early metadata, there was all the stretch for the individual detectors or flowCores themselves, and then we reached a section of the middle metadata, which is where we start seeing the very last of those kind of $ keywords associated with them. And kind of enough, you can see there's some of those things as far as experiment name, project name, you see those values appear. You actually see where the compensation adjustment spillover matrix is stored. It's stored as an actual matrix associated with your keyword, which is how you're able to retrieve it after the fact on some instruments if you did do compensation on a conventional flow cytometry file. And as you continue scrolling, you can see this was 64 detectors or so it was quite a bit, and just repeats down. And then, of course, you can see what's compensation applied. You can see version of software. And at that point, you start leaving the actual $ in the name of the actual keyword itself. So those tick marks are no longer needed, with the exception if you have a space present in the keyword, in which case you still need to apply these little tick marks on each side of the keyword. And these were just ones I mentioned in passing. There's a bunch of keywords that if you were interested in them, you could retrieve them from that description list now that you know they exist. You don't actually need to memorize all these because there's no actual meaning of things. And you can see we have the volume for this particular file that was acquired. And the actual keywords that are encoded does vary a little bit by which manufacturer is using the made the instrument. And some of them will be exactly the same thing being measured, but just provided with different keyword names, which can be quite annoying because it's not standardized. And yeah. This is the last of the middle metadata. After the middle metadata that's more associated with your individual file, you do find this additional set of stretch of metadata that's associated with your individual lasers, as far as like what delay was set for the lasers, what was the area scaling. Some manufacturers will also say a little measurement of laser power. This is something that we also end up plotting for our RQC website just because it can be useful to like try to correlate what's happening on a particular day. And then there's it's a really large stretch of basically every single detector. Basically, this is what's used by the commercial software of knowing, do you need to like visualize this in linear or log scale? It's not something that you're going to interact with directly, so it's most of the time ignored. And then the very final detectors in that particular list are very much some of your final settings that you would do on an individual experiment, like what was the threshold set at, what was the tube name, what were your user settings, and what was the window extension on that particular day. So if you had done the initial setup as far as our code, and we had read in the actual FCS file setting transformation is equal to false and truncate is equal to false, that's the end of the keyword section. But one thing I noticed when we were actually like going through the course and getting things set up is the actual number of keywords changes when you set transformation is set to true instead. In this case, so when we run our initial read.fcs file, we don't actually have transformation set to true. When I'm asking it to give me these index positions after the final window extension keyword, it's returning us null values, which basically stands for it's non-existent, there's nothing present. However, if we had set the initial operation as transformation is equal to true, and then we went in and checked to see the keywords, there's an additional stretch of keywords that appears, the flowCore keywords, which are basically the conversion as far as like what has been applied by the flowCore package as far as transforming your values for particular locations. So this is mostly just a footnote kind of style, except if you're working with some of the unsupervised analytical packages that we'll be dealing with later on in the course, You'll notice if you ever export out the normalized data and you're bringing it into FlowJo or FCS or another commercial software, and you open up and check the keywords, you'll see these flowCore parameters are still present, even though you have always set all your transformations to false. The reason for this is somewhere within the actual package that you're using to do the normalization, it has a transformation implied set to true. So all these keywords are being added in and are kind of perpetuating downstream. So this is just kind of like one of those index of it's useful to kind of keep an eye on what's happening with your particular files, because even though you think it may not be changing, it can be read and you can see changes happening in your files downstream, which potentially could be useful for you later on to know about. So with that, we have made it through our deep dive of what's within and inside an FCS file when we read it into R as a flowFrame object. So we see that within these larger, more complicated objects, which are known as S4 objects, which are very common within bioconductor packages, a lot of the more simpler object types can also be present, things like matrices, things like data frames, things like lists. So we are actually able to go into these complicated objects and retrieve these individual things that may be of interest to us and save them as particular objects or variables within our R environment that we're then actually able to use. So this is not something that's going to come as far as like ease of figuring out how to navigate these things overnight, but it's a skill that we'll build on throughout the process. So this exploration kind of workflow, like what we just did, is very much what everybody as a beginner starts off by doing. We explore these bits by pieces, we try to figure out what's going on, we build context cues, we may search some documentation until we get a bigger idea of like what we're actually trying to grab and what we're trying to do. Because when you have a goal, if you want to be able to do something, that oftentimes is the motivation, the catalyst to actually being able to accomplish it. And then continuing our analogy that we've been working with for the last couple of weeks, if all the functions within R are basically tools and a package is a toolbox, we need to be able to hand these particular tools the objects they need, the object types that they need in order so they're able to carry out their work. So if the particular type of object is a matrix, and let's say your matrix is kind of standing for a paint, you would need to hand it to a tool like a paintbrush to be able to actually use it when it comes to painting your wall. Versus if the object, a matrix, is kind of like paint, you're not going to hand it to your hammer because at that point your hammer's not going to be able to handle it and it's just going to return an error. So this is kind of like understanding the context as far as like what are you working with in terms of particular tools or functions, but then what kind of objects are you working with in terms of type dictate like what your decisions are as you navigate throughout actually carrying out a coding workflow. So next week, prefacing what we're going to look at is we're going to dive into tidyverse packages, which are those R packages that have made working with R much more pleasant of an experience over the last 10 to 15 years. They are particularly focused in on the two types of objects we encountered today when we're diving into those particular flow frames, matrices and data frames. So the basic premise of the tidyverse is it's good to keep all your data showing as rows and columns. And the reason behind this is explained within the tidy data paper, which I have linked below. It's one of those things that started to click for me as far as like how do we work with things in R after having read this paper. So I'm looking forward to next week just to share those with everybody else. I realize we're at the top of the hour, so I'll let anyone who needs to go. As far as additional future reading, the main resources I provide for today are going to be the data file standard for flow cytometry, especially those 3.1 files. This is for anybody more wanting to nerd out about the actual FCS values that are present within these files. If vectors versus lists was not particularly intuitive for you from my explanation of it, I included a video that's on YouTube that does a pretty good job of explaining the differences and also talks a little bit about the coercion side. And then for those of you who are looking more of a bigger view of like, okay, we worked with those intermediate type objects, which are known as base types, and we also worked with these S4 objects, which are the more object-oriented types. Hadley Wickham's Advanced R book does a good chapter as far as the overall view of what's going on. If you want to do optional take-home problems this week, it's going to be a little bit lighter compared to what we did last week, just because you are going to need to like actually open FCS files and kind of like deep dive them yourself. So what we went through for today was very much just a raw spectral flow cytometry file, but within the subfolder of the data folder for this particular week, there's also an unmixed file, the 2025_07_26 ... for the continuing. So you can also repeat the same process for this unmixed file, and you can report back to say, these are the main changes I noticed. Similarly, not everybody's working with spectral flow cytometry files. So if you're working with a mass cytometry file or a conventional flow cytometry file, you can explore that same process and see how they change it. We also noticed somebody had a cytoflex, and their parameters are very much not what we were expecting. So if you do encounter anything funny, just go ahead and post that on the discussion page. And then the very last one is kind of do the same process we just did as far as exploration. If you have commercial software, open up an FCS file in the commercial software, see what you're able to see. If you don't have a commercial software license, what you can do is open it up in flowRayata.io, which I linked the pre-course walkthrough in the actual question itself, and just kind of try to figure out what kind of keywords, how you get about these keywords as well. And with that, I'd like to thank you for your attention and spending your hour of your afternoon with us. And if you have any questions, please pop them in the chat. I'll be here for a little bit, and if you don't have any additional questions, I will see you next week, or I'll address any questions that you may have or looking for additional insight in the discussion forum throughout the week.